All right, so a reaction shift, this all is basically Le Chatelier's principle, figuring out which direction it's going to go. And again, I think the best way to approach this is with the three-column chart. You have the stress that is initially applied, the way that the system will respond to that stress, the response, and then what is the actual result? Which way is it going to shift because of this? So the stresses basically get us started, and then we're going to figure out the response, we're going to figure out the result. So in this case, the stress is some A is removed. The response to a stress is always the exact opposite. If we remove some A, the response is going to be to replace that A. So we say to ourselves, all right, which direction does this reaction need to go to replace the A? Are we going to go to the left, breaking the C and D down to make A and B, or are we going to go to the right, breaking A and B down to make more C and D? Well, if I want more A produced, I'm going to go to the left, because that is going to make more A at the expense of C and D. The next stress on the system is some B is added. So if some B is added, the response is to remove that B. Again, it's always the opposite. Which direction do we go to remove the B? Actually, I should catch something here, and I might have missed it before. B is a solid. And if we think about what Q is defined as, or K, C times D over A. B is actually not part of this because it's a solid. Its concentration never changes. So you might find this odd, but because B is not part of the K equation, adding B will not change Q, it won't change K, so it turns out there's actually not going to be any change as a result of B added. And that's a little confusing, and the bottom line is to notice that if it's not something that's in the equation for K or Q, it's not going to make a difference, so there's no change there. All right, how about C is removed? So we want to then replace the C, and to replace the C, we're going to have to go right. Next, the reaction vessel is cooled down. So one thing I didn't mention here, this is exothermic, so we have a heat term. And if it's an exothermic reaction, we can say the heat term is on the right. So if I am cooling down the system, let's translate that, I'm removing some heat. So I'm just going to write remove heat. So if I remove heat, I want to replace the heat. That is my response. So which direction do I go to replace the heat? I'm going to go where the heat is. I'm going to move to the right. All right, lastly, the volume is decreased. Let's translate that. That means if I lower the volume of the container, I'm actually increasing the pressure. So what is the response? I then want to lower the pressure. So the way I lower the pressure is I look and I try to find out how many gas particles are on each side, because that's going to determine which way I can go to reduce the pressure. So how many gas particles are on the left? Turns out 0. There are no gas particles on the left. On the right, I have 1. So I'm only counting gas particles. So if I want to lower the pressure, I want to go to where there are fewer gas particles. In this case, that is going to be to the left. So some really good problems in this one. It hits on a lot of points. I know a couple of these are confusing, particularly number 2. This idea of a solid or a liquid not actually affecting a shift. Just keep an eye out for that. But otherwise, this is pretty much what you can expect from a Le Chatelier's problem. Okay, so until next time, I am Derek Genova. Have a delightful day.